Well, welcome to this flipped classroom video. Today we are going to talk about finding the domain of a function. Maybe I can put that at the top here. Not just what the domain is, but finding or determining the domain of a function. We'll start with a couple of vocabulary words and then just simply go through a few examples. Remember that in general, the domain of a function is the set of all possible input values. And those are generally the inputs that create outputs that are real numbers, where I don't end up with imaginary numbers, I don't end up with empty sets, but where I can put in a number and actually get out some sort of answer. Generally, our domains, the way we present our domains, fall into two categories. One being that the domain is stated explicitly. And that means that the domain, that set of numbers, is actually written next to the function. And, oops, excuse me, lunch bell. What that looks like is, instead of simply saying f of x equals, let's say, x squared minus 4. Let's say that's the function we're dealing with. Next to it, we'd have a comma or a semicolon or something like that. And we might write next to it, x is greater than 3. And what that means is, for this function f, we only want to use inputs that are greater than 3. So it's actually written out next to it, telling you which ones, which values, which inputs we can actually use. And that happens sometimes with domain restrictions on certain functions. What, however, is more common is a function to be stated implicitly. And that means that the domain is not stated and actually written out next to it. It's simply implied. And it's implied by what we might call natural restrictions. And that's where we would be doing things like we would avoid negatives under radicals and zeros in denominators. For example, if we had the function f, let's try a different color here. If we had the function f of x equals the square root of x, and we just had that function, there is no domain stated next to it over here. It's nothing there. But we just naturally understand that the value of x cannot be negative, because you can't take the square root of x. So we know that x has to be, you can't take the square root of a negative. So we can only take the square roots of positive, the square roots of 0. It doesn't need to be stated, because that's just kind of a rule of algebra. And that's one of those things that is implied by a natural restriction. It just is the way it is. And that's how most functions are going to work, and we just have to be aware of that. Most of what we're going to do, though, is practice turning implicit domains into explicit domains, so that we know how to read and look at functions and get used to recognizing those natural restrictions. So that's what mostly we're going to be working with here. Okay? Okay. So continuing here, there are really only two things to check when finding an implicit domain so that it can be stated explicitly. And I put them on the last slide. I'm going to put them on this slide as well. But we must avoid inputs that create zeros in the denominator, because you can't divide by 0. We also must avoid inputs that create negative values under even radicals. And what I mean by even radicals are square roots, fourth roots, sixth roots, etc. Things like that. So if we can avoid those two things, avoid inputs that create zeros in denominators, and we can avoid inputs that create negative values under radicals, we will know, knowing what we want to avoid tells us what we want to keep, and we just go from there. And it's just really some basic algebra. So we're going to just jump into 3 examples to demonstrate that right now. So here's our first illustration. Determine the domain of each function. If I look at this function f, it's defined as x cubed minus 4x squared. So the 2 things I had to look at. The first thing was zeros in denominators. Well, in this particular case, this function has no denominators. The x cubed, the x is not in a denominator. The x squared, the x is not in the denominator. So in this particular case, we have no denominators. So we have no restrictions. And it's all good. I check the second thing I have to work on are negatives under even radicals. Well, like for our denominators, we don't have any radicals. We have powers, but we don't have any root symbols. So no radicals means no restrictions, which means we can use any real number that we want for x. They're all fine. They're all perfect. And so there's a few ways of writing it, depending on what your instructor might ask for. I generally start with a capital D and a colon to stand for domain. And in this particular case, I would write x. I would use the element symbol, and then the blackboard R for real numbers. X can be any real number. Also acceptable, a different version, but also acceptable, would be x is an element of the open interval from negative infinity to positive infinity, if your instructor likes you to use interval notation. Just saying we can use every number between negative infinity and positive infinity. It's the same as saying all real numbers. 2 different ways of saying the same thing. I'm going to put an or right there. So that function f has no denominators, so no restrictions. No radicals, no restrictions. We can use anything. And that does happen. Our second example. G of x equals 2 over x squared minus 9. I don't see any radicals in this, so no radicals. So I don't have to worry about that. No radicals. So no restrictions there. But I do have a denominator, so I have to make sure that I don't end up with a 0 in the denominator. So what I would do is I would take my denominator and I would set it equal to 0, thinking to myself, I got to figure out which values of x would make my entire denominator equal to 0. And the honest truth is that if that happened, if x squared minus 9 equaled 0, that would actually be a bad thing if that happened. So I go through and I'm going to solve this. X squared minus 9 equals 0. I'm going to add 9 to both sides. X squared equals 9. Take the square root of both sides. X equals plus or minus the square root of 9, which is plus or minus 3. Now don't forget, we said that this would be a bad thing. So I'm going to put that next to there. So x equaling positive 3, x equaling negative 3 would be a bad thing. All of the other numbers in existence would be fine. So how do I write down the domain is everything except plus and minus 3? Once again, a couple of different ways to do this. One way to do it would be just simply to write the domain x cannot be plus or minus 3. That's one way. Or in interval notation, the domain could be, well, I'd start at negative infinity, get to negative 3, stop. I can't include negative 3. Pick up on the other side of negative 3, go to positive 3, stop. Pick up on the other side of positive 3, and then go to infinity. So in this case, I've got a triple interval starting at negative infinity, stopping at positive infinity, skipping negative 3 and 3. It's kind of an awkward way of writing it. Maybe not the best way of writing it. Definitely not efficient. Or using set notation, I could say x is all real numbers except, and we would use a curly bracket here, plus or minus 3. That's saying if we think of this as a group, the group of all real numbers. And from that collection or that set of all real numbers, take out from it, not like an arithmetic subtraction, but like an actual removal of the two numbers plus or minus 3. So I start with every number and I remove plus and minus 3, so it's everything except. And that's another way of writing it. We'll talk more in class about these 3 ways, but we're going to work on some notation, some more sophisticated ways of writing it. But those are 3 ways of writing that domain. More importantly, twofold for this whole problem. Let me do a full screen here. There's 2 parts to it. One part in blue, finding out what numbers are good and what numbers are bad. And then in purple, the second part, how do we write that down? So we have that. One last example, h of x equals the square root of x minus 5. Here I'm going to start by saying, hey, I've got no denominators. So I have no restrictions from there. But I do have a radical, so I have to address that. And I cannot have a negative under a radical, meaning that this expression, the x minus 5 piece of that, cannot be negative. Well, if it can't be negative, there's no symbol for can't be negative, that means I want it to be either positive or 0. Not negative means positive. Not negative could also mean 0. So greater than or equal to 0. Add 5 to both sides. So x would have to be greater than or equal to 5. So the numbers that work, the numbers that are acceptable in the function h are all the numbers that are greater than or equal to 5. So I guess we suppose that we did the first part, which numbers are good, which numbers are bad. Now the second part, how do we write that down? Capital D for domain with a colon. And one way is using inequalities. I could simply write it. If I'm going to use interval notation, which is definitely gaining favor in the world today, in the math world, we use intervals a lot more. I would write x is an element of, and I'd start with a closed interval at 5, so that I'm including the number 5, comma, I want all the numbers that are bigger than 5, and I want to go forever, and that would get a parenthesis there. And those are the 2 ways that function could be written. Okay? All right, so so a few important things from the video. If you need to go back and review them, go ahead. Otherwise, we'll do some more practice in class. What a domain is, what explicitly stated and implicitly stated domains are. And then when you're actually doing the problems, 2 things. Being able to figure out which numbers are in the domain, which numbers are out of the domain, and then how do we represent that. I hope you got this. Hope this was helpful just to get you going. We don't need to be perfect right now. We'll pick up with more of it in class. Thank you.